This video is a lesson for Precalculus on Chapter 6, Section 3, Parametric Equations and Motion. What we'll be doing today is I'll talk to you about what parametric equations are and also different ways in which we'll use them. By the time we're done with this chapter or this section, you should be able to define parametric equations, graph curves parametrically, and solve application problems using parametric equations. We'll start with our definition. A parametric curve or parametric equation is the graph of the ordered pairs xy, where x equals f of t and y equals g of t are functions defined on an interval I of t values is a parametric curve. So basically what that's saying is when we graph x and y, each one of those are some function of t, where the interval I of t values, that's just saying I'm going to plug in this range of t values in to each the x and y functions to get my coordinate points. So when I plug in the same value into the x equals f of t function as I do for the y equals g of t function, plugging into both of those gives me just one coordinate point xy that I would then graph. The equations are parametric equations for the curve. The variable t is the parameter, and I is the parameter interval. What we will now do is I will show you on your calculator where you can plug in these different equations. So if you go on your calculator, obviously you turn it on. What you'll need to do is press your mode button. And once you're in that mode area, you can click down, and what we want to do is we want to change from function to parametric. So you just press over and enter, and now you're in the proper mode. If I now press on the y equals button to set up a graph, you'll notice I've got a spot for both an x equals equation and a y equals equation, and that's what I want. So what we'll do now is we'll just practice graphing a parametric equation. Now, oftentimes what parametric equations are used for is to apply another variable to whatever we're working with. A lot of times the t will represent time, where x will represent a horizontal distance and y will represent a vertical distance. But that's not always the case. They could represent different things. What I want you to do now is type into your calculator x equals t squared minus 2 and y equals 3t. And then what we're going to do is we're going to see what graph we get on the t interval, -3 to 1, and then we'll see how that's different from -2 to 3, and compare that to -3 to 3. So go back to your calculator and type in x equals t squared minus 2 and y equals 3t. What you'll notice is the button that you use for your variable x normally, that also has a t on it. That's because you can use that same button now in parametric mode to type in a t. So the first graph that you're supposed to print uses a t interval of -3 to 1. So if you go back to your calculator and press your window button, that's what it's asking for first. We want a t minimum of -3 and a maximum of 1. Double check that. -3 to 1. Yep. So now the next one, it says t step. Basically what that means is it's asking how often do you want them to plug in a t value. So do I want to plug in -3 for a value and then -2 and then -1 and then 0 and then 1? That would be a t step of 1. Well, if I did something like that, it's only going to plot those points. What I'm trying to do is I'm trying to find what the graph looks like. So if I want it to look like a nice flowing graph that doesn't have a bunch of holes in it, I want the t-step to be smaller. So you're going to have to use some judgment on that and maybe some trial and error. I'm going to start with just 0.1 and see what that does. Our x minimum and maximum is the same as it was before. We'll just start with a negative 10 to 10 window for the x values. A scale of 1 sounds fine to me. And then a y minimum of negative 10 and a y maximum of 10, just like the standard window is, and then the y scale of 1. Go ahead and graph that, and that's what your graph will look like. This is the graph that you get when you have your t interval of negative 3 to 1. Those are the x, y coordinate points you'll get back. Now, when you change that to negative 2 to 3, let's see what happens. Go back and change it from negative 2 to 3. You should get a little different looking graph. If you notice, it does look different. I'll show you what the difference is here. I'll put the graphs side by side. These are the differences. And then I've also graphed negative 3 to 3. So you can see how if you change your interval for t's, it'll change where it graphs on your coordinate grid. And then obviously, the larger your interval is, the more graph you'll have, especially in this type of case. Now that will change or could change when we get into using trigonometric functions, because there, if you have a larger interval, well, that just might mean you're going around the circle more than once. But we'll get into that in a little while. We also will have problems that are called eliminating the parameter. When a curve is defined parametrically, it's sometimes possible to eliminate the parameter and obtain a rectangular equation in x and y that represents the curve. That often helps us identify the graph of a parametric curve. So basically what I'm saying is I can combine these two equations into one, and in so doing I might recognize that this parametric equation can also be represented by another equation, whether it be a circle, a parabola, a line, something like that. So in order to do that here, what I would do is I would try to set it up using substitution. So I would want to solve for t on one of the equations, like I'll take this x equals t plus 1. If I solve for t by simply moving the 1 over, I would get t equals x minus 1. Well, now I have a value for t, so I can now take the other equation, substitute x minus 1 in for t. So then y would equal 2 times x minus 1, which means y would equal 2x minus 2. You know what that equation is. That's the equation of a line that has a slope of 2 and crosses the y-axis at negative 2. Since the interval, the t interval, is from negative infinity to infinity, this is going to be a graph that goes on forever, and thus it is the graph of the entire line y equals 2x minus 2. If you were to graph x equals t plus 1, y equals 2t, that parametric equation, you would get the same result as y equals 2x minus 2 on your regular coordinate grid. If we do not specify a parameter interval for the parametric equation given, it's understood that the parameter t can take on all values that produce real numbers for x and y. We will use this agreement or this understanding in this next eliminating the parameter example. I had my slides out of order there for a second. So here's the parametric equation I wanted to use. So we will use x equals 5 minus t squared and y equals 6t. So again, first thing we'll do is isolate a t value. What I'm going to do is solve the second equation for t. So by simply dividing by 6, I get t equals y over 6. I'm going to then substitute that result into the first equation. So I'm going to take y equals 6 and plug that in to replace the t in the x equals equation. And the main reason I chose to do that instead of solving the x equation first is because if I solve for the t in the x equals 5 minus t squared equation, I would end up having to use a plus or minus square root value, and that's not quite as neat as doing it this way. So when I substitute that back in, I get x equals 5 minus y squared over 36. Well, now I can isolate the y value, or the y squared value in this case, and I get y squared equals negative 36 times quantity x minus 5. Well, that tells me I have a parabola, a graph of a parabola that opens to the left and has the vertex of 5, 0. I can show you the graph of this here by graphing that parametric equation. It matches up with what I've just described. On this next example of eliminating the parameter, we have a parametric curve defined as x equals 3 cosine t, y equals 3 sine t on the interval of 0 to 2 pi. Now, you understand trigonometry and you know that that variable t is going to represent an angle. So right now, if we're going from 0 to 2 pi, obviously your calculator needs to be in radian mode. But also, what you'll want to start recognizing is what type of graphs these are going to create. And if I graph this, so 3 cosine t, 3 sine t, what I end up with, okay, so I'll plug those in just like normal. I'll go to my window, and what I want to do is I want to make a square window. So what I can do, first of all, for my t min and max, I want to go from 0 to 2 pi. So I would type in 0 for my minimum, and my maximum would be 2 pi. You just type in a 2 and then use the second caret button to get the pi symbol. When you press enter, it'll convert it to a decimal. My t-step, I'll just leave at 0.1. And then for my x minimum, I know if I go from negative 4.7 to 4.7 for my x min and max, and I go from negative 3.1 to 3.1, that's a square window. So maybe you want to jot that down in your notes so you remember that. And then multiples of that will continue to get a square window. My x scale and y scales are going to be 1. When I graph this, I get what basically looks like a circle, and since my x scale is 1, I know that I have 1, 2, what looks like 3 as a radius. So that's what I'm going to try to prove. Well, when I'm trying to prove that, I know that x squared plus y squared is the equation of a circle. So I'm going to plug in 3 cosine t squared plus 3 sine t squared and simplify that, which is going to show me I'll get 9 cosine squared t plus 9 sine squared t. Well, if I factor out a 9, I have cosine squared t plus sine squared t what do you know about cosine squared t plus sine squared t? Well, you know it equals 1, which shows we have the equation of a circle with a radius of 3. What you can do now that's interesting is since the interval that we're using is from 0 to 2 pi, it'll trace all parts of the circle. If you increase that to greater than 2 pi, what it'll do is it'll just trace that circle more than once. Decreasing the interval, or the length of the interval, will only give you part of the circle. So maybe you want to experiment different parts of the 0 to 2 pi to see what shows up on your grapher. That's good times. So the last example I'll go through is finding the parametric equation for a line. If I want to find a parametrization of the line through the points A is 2, 3 and B is negative 3, 6, basically I'm going to go through the same process every time. I've drawn a sketch here to kind of give you an idea of what we're talking about. What you need to realize and know is if you let some point P, x, y, which is what we have here in green, be an arbitrary point on the line that goes through line AB, which we're trying to find the parametric equation for, then vector OP is the tail-to-head vector sum of OA and AP, where AP is a scalar multiple of AB. And all of these we're talking vectors. Let the scalar be t, so some variable t, or some number t, so it's a variable to us right now. And if we do that, we get this vector OP equals vector OA plus vector AP, which is going to be the same as vector OA plus some scalar t times vector AB. Well, what all that means to us is we can treat this just like we can treat this like vector addition, because what this is saying is if we take, try to use some highlighters maybe here to help give you a visual, we know that OA, vector OA, plus vector AP, which we don't know quite where that is going to be the same as OA plus some plus AB times some scalar t. How do we know that that's true? Well, this is going to be a right angle formed here, and we know that the hypotenuse, if you will, of the vectors formed is the sum of those legs of that right triangle formed with vectors, as we talked about in section 2. So with all that said, that explanation, here's the work involved. You're going to take the initial value as a vector, 2, 3, because we're going from the origin 0, 0 to 2, 3. That's going to give us vector 2, 3 plus t times vector AB. Well, we just use the heads minus tails rule to get that vector. So we take negative 3 minus 2 and 6 minus 3 to get the other vector. Well, once we do that, we can add them together and we would get, well, 2 plus t times negative 5 is 2 minus 5. 3 plus t times 3 is 3 plus 3t. That then tells us that x equals 2 minus 5t, y equals 3 plus 3t, when we have the interval from negative infinity to infinity, will give us the line that we've been looking for. If we change that, so this with, oops, I'll write this in a different way. Negative infinity to t to infinity, that gives us the equation of a line. If the question were changed to find the equation to give us the line segment, well, I would write this the same parametric equation, but the line segment A, B would be the parametric equation given, but I'd have to change and use the interval from 0 to 1. That would give me just the line segment. But when I use from negative infinity to infinity, I get the entire line. That's the first lesson on 6.3. The second lesson will then apply some real-life problems and word examples.